All right, we're back. Sorry about that. Looks like my operating software was trying to push an update to me. All right, we left off by talking about this problem here, in which we are going to, we said, solve by isolating the radicals. So we have one on each side, and we said, try to get the more complicated one by itself. Not that it matters, it's just nicer when we go and FOIL or box method everything out. So what we're going to have to do is square both sides. This side is going to be really nice. It's just an x minus 12. That's why we say get the more complicated radicand isolated. But then the other one we're going to have to box method. Now as I set this up, we get an root x times root x is x. Negative 2 times negative 2 is positive 4. Then I have a negative 2 root 2. I'm sorry, negative 2 root x and a negative 2 root x. So our answer, when we go through and combine the like terms, I have an x, I have a positive 4, and then negative 2 root x and negative 2 root x is negative 4 root x. So we can see here, I like to group the things that aren't in radicals together. We can see here that we've gotten rid of the one radical, and now we just have to get rid of the next one. So all we have to do is repeat the process of re-isolating the radical. So I'll subtract x from both sides, and then I'll subtract 4. We end up with a negative 4 root x equaling, well, the x's cancel out, and we have negative 12 and negative 4 is negative 16. I can then divide both sides by the negative 4. You don't have to, but why not, right? So we have root x equals negative 16 divided by negative 4 is just positive 4. So we can square both sides, and we end up with x equaling 16, positive 16. So make sure that you're comfortable with all these steps. Again, really be comfortable working with these two radicals. It's not that hard. You just have to keep squaring, right? When in doubt, just keep squaring both sides, and eventually you'll get all of the radicals to, in fact, cancel out. So let's check our work here, and let's see if this is going to be a solution, or is it going to be extraneous? So I'm going to plug it in. I have the square root of 16 equaling the square root of 16 minus 12 plus 2. The square root of 16 is 4, and the square root of 16 minus 12 is the square root of 4 plus 2. All right, well, the square root of 4 is 2, and when I add 2 and 2 together, I get 4. So it works. 16 is, in fact, going to be a full solution for us. Again, I always say plug it into the original problem because you don't want to plug it into the simplified version because the simplified version would have a different domain than the original, okay? Let's try one more of these. This was a much more complicated one from the advanced practice. Required a couple different steps to go about simplifying this. I'd like to review this one, and then I'd like to get into today's topic of section 11.1. Again, if you have any questions or things you'd like me to go over, please let me know over in the live chat. I'd be happy to go over anything you need me to review, or if you need me to slow down or re-explain anything, just let me know. In this problem, again, we have two radicals. Not a big deal. We usually would say get one of them on each side. And again, is that necessary? No, it's not. But it just makes our work easier. One of the things that I would say here is notice that we have a 6, a 3, and a 3 as kind of the, I would say, the coefficients. They're not really coefficients, but as these numbers being multiplied to everything, a 6, a 3, and a 3. Can I factor out a 3, a GCF from each of these? Let's see what I'm left with. A 2 plus a root 3x plus 1 plus a root x minus 1 equaling 0. I kind of treated this whole thing like a polynomial, and I factored out the GCF of 3. And this is totally fine because watch, redistribute. You get right back to where you started. So I could factor that 3 out, so I'm left with a 2 plus the square root of 3x plus 1 plus the square root of x minus 1 equaling 0. This is the thing that I want to solve. Did you have to do that? No, you didn't have to. In fact, if you didn't, that's totally fine. You get the same answer. You'd actually simplify what I just did just a little bit later. But I figured, why not give it a little try? So again, all we need to do is square both sides. Does this look nice and easy to square? No, I don't want to set up a box method like this. Instead, what I'd like to do is get at least one of these radicals to the other side. And I'm going to pick the one that has I'm going to try to isolate the one that has the more complicated radicand. This looks a little more complicated than that. Okay, so I'm going to suggest we get this one by itself. So I'm going to have root 3x plus 1 on one side, and the other side I'm going to have a negative root x minus 1 and a negative 2. I just subtracted the other things over, okay? Now, let's square both sides. My goal is to get rid of the complicated radicand. So I'm going to square both sides, and again, that gets rid of the complicated root. So I'm left with just the radicand 3x plus 1. The other side, well, I'm going to need to do box method for this. So let me set that up down here. And this is why scrap paper is really important, or having very organized work, because you can see how each of these equations that we're working with, the process really just continues to pick up more and more and more. So negative times negative is going to be a positive, and I have the square root of x minus 1 times root x minus 1. Well, that's just x minus 1. And then negative 2 times negative 2 is positive 4. Now let's take a look at the corners. Negative 2 times negative root x minus 1. Well, the double negatives make a positive 2, and then I have a root x minus 1, and then I'm going to have the same thing here. So let's see what we end up with. I'm going to first look at the real components. X minus 1 and a positive 4. That's just going to be x plus 3. Now let's look at the radical components here. I have a 2 and a root x minus 1 and another 2 root x minus 1. So that's going to be 4 root x minus 1. Again, we just combined our like terms. This is what we end up with. And this is what we expect to end up with. We perform this operation where I have radicals on both sides. I expect to only cancel out one at a time, and that's fine. Now we're still left with a square root of x, so all we have to do is just square again to get rid of that. Let's make it a little easier on ourselves. Let's combine some of these like terms. I'm going to subtract the x over, and I'm going to subtract 3 over. We end up with a 2x, a negative 2, and that's going to be equal to 4 root x minus 1. I could go ahead and keep simplifying this if I wanted to, but it's not necessary. You could divide both sides by 4, for example. I wouldn't necessarily, just because I don't want to work with fractions at this point, but you could. Instead, I'm just going to leave things as they are. Some people might say you could divide both sides by 2 and get an x minus 1 equaling 2 root x minus 1. That's fine. I don't know. I figured I keep doing that, so I might practice an example or show you an example where I don't move this value over. And let's see what we end up with. I'm going to square both sides. On the left-hand side, obviously, I'm going to need to do box method because I have a binomial and I'm squaring it. I end up with a 4x squared, a positive 4. Here I'm going to have a negative 4x, and here's a negative 4x. So I end up with a 4x squared, a minus 8x, and a positive 4. That's what I get when I square things or multiply them on the left-hand side. Now, the right-hand side, well, let's just square everything here. 4 squared is 16. And then x minus 1, the root of that squared is just x minus 1. So when we fully simplify, we get 4x squared minus 8x plus 4 equaling 16x minus 16. Notice I can distribute it here. I couldn't distribute it before because it was in a radical. But once I got it out of the radical, then we can distribute things through. Now, we did all of this work just to get rid of the two radicals. Now, what do you notice about our solution? Well, hopefully you're saying that's a quadratic. That's a degree 2. So really, I have a quadratic equation to now solve. So let's subtract 16x from both sides. And then let's add 16 to both sides. What we're doing here is we're saying if we have a quadratic to solve, we're going to need to go ahead and use the zero product property. So that's a negative 24x plus a 20 equaling 0. All right, all of this work was just to get our equation into something we can solve. We got our radical equation into a quadratic. Okay. Does this always happen? No. We just saw several examples where we took our radical and it turned into a linear equation. It just so happens in this particular example, it simplifies to a quadratic. But that's fine. We have methods of solving this. So let me get some space here. And let's see. We had a 4x squared. I think it was minus 24x plus 20. And that's equals 0. This is the thing that we're going to need to now solve. And that's okay. We have the zero product property, but I'd also like to take a minute to do an alternative method that we're learning about today, and that's completing the square. We're going to take today and tomorrow to learn 2 other methods for solving quadratics. So let's go ahead and let's solve this by the zero product property. The zero product property says factor this polynomial down and set each factor equal to 0. Well, hopefully you're noticing before we factor things down, because we could go ahead and start doing a C method, notice that there's a GCF in here, and that GCF is 4. So I'm going to factor the 4 out. I get an x squared minus 6x plus 5 equaling 0. Okay? It's always helpful to first look for a GCF, and if there is one, just factor it out. So really the thing that I need to factor is x squared minus 6x plus 5 equaling 0. This is the thing that will have solutions that get me 0. So let's factor this down. I have 2 binomials. What multiplies to give me 5 but adds to get negative 6? I'm thinking negative 5 and negative 1. That would multiply to get me positive 5 but add to get negative 6. Both of those are going to be set equal to 0. So I have x minus 1 equals 0 and x minus 5 equals 0. So solving, I get x equals 1 and x equals 5. These are my 2 possible solutions for this quadratic. Now, we have to go and check our work. We got to make sure that they're in fact both solutions. Notice though, when I check this work, I am plugging these solutions in to the original equation. I'm not plugging it in to the quadratic. I am not plugging it into the quadratic. I know that they work for the quadratic. I know for a fact that they'll work for that. What I want to know is, do they work for the original? Remember, quadratics have an infinite domain, negative infinity to infinity. This doesn't have any restrictions on it. This original one, oh, that does have restrictions on it. There are certain things we can't have in the real number system for that. So let me go back and plug everything in. Let me just try to copy this down really quick. We had a 6 plus 3. Oh gosh, now I need to remember what this thing was. Let me change colors here. It was a 6 plus 3 root 3x plus 1 plus 3 root x minus 1 equaling 0. What I want to do is take time to check each of these values, and let's see what we get. I'll try to fit it to the side here. 6 plus 3 times the square root of, well, 3 times 1 is 3 plus 1. And we have the square root of 1 minus 1. That's for the value x equals 1. Now let's check for x equals 5. 6 plus 3 times, okay, 3 times 5 is 15 plus 1 is 16. And then plus 3 times root 5 minus 1. Okay. Let's start on the left. We have 6 plus 3. 3 plus 1 is 4. And 1 minus 1 is 0. Okay? That's just going to cancel out. Now, let's say 6 plus 3. And by the way, this has to equal 0. Oops. I better make sure I write that. Equals 0. That's what we're supposed to be checking. So we have 6 plus 3 times root 4. Root 4 is just a 2. So we have 6 plus 3 times 2 is 6. That doesn't equal 0. So this solution is extraneous. Again, some people might be saying here, wait a minute, Linford, wait a minute. The square root of 4 is positive 2 or negative 2. If you took the negative version, it would work. But again, we don't want to leave it to, it works for one, it works for the other. The first root we always take when we take square roots is the positive one. And that's really what we're using to evaluate things. Now let's take a look at 5 here. 6 plus 3 times, the square root of 16 is 4. And then 3 times 5 minus 1 is 4, so that's the square root of 4. We have 6 plus, that's a 12. 3 times root 4 is 2. So we have 6 plus 12 plus, well, that's just a 6 again. So that's 12 plus 12, which is 24. That doesn't equal 0 either. So it turns out both of these solutions are extraneous. And that's possible. That's totally possible. If you look at the graph for this, you would actually see that its graph doesn't cross the x-axis at all. There's no value that if you plug in for x, you get the output to be 0. So make sure you're comfortable with problems like this. This is a much more elaborate problem, but something you might see on a test. The idea here is we solved it like normal first. We solved it like normal, where we squared one side, then we squared the other, and then we had to solve the resulting quadratic. And we used that by the zero product property. And we got both solutions actually to be extraneous, so neither solution worked. So there really isn't a real solution for this problem, and that's fine. Sometimes these equations don't have real valued solutions. Now what I'd like to do, I want to get into the topic that we're talking about today, completing the square. I'd like to do 2 problems from this section, and then I'd like to go back and resolve this problem, but instead of doing the zero product property, I'd like to do the completing the square method. Let's first start by introducing the idea of completing the square. Completing the square is a way of solving a quadratic equation. Okay? You had the zero product property. Now we have completing the square. And you might say, well, what's the point of that? Why do we have completing the square? Well, let's try to solve this problem using the zero product property. I need to factor this down and set each of the factors equal to 0. All right? What multiplies to give me -1, but adds to give me 4? Oh. Nothing. I don't think. Let's see. What gives me -1? Well, that's just +1 and -1. But those don't add to 4. Here's the problem. This polynomial that we have is prime in the integers. It's not going to work in the integers, meaning you can't factor it down with integer values in the factors. So the zero product property isn't going to work here. We need a different method. And this method is called completing the square. Completing the square is a valid technique for solving any quadratic you have. You can solve any quadratic by this method. It's just the zero product property is kind of nicer when we can in fact factor it down. So let's go ahead and try this method. I'm going to explain the process fairly quickly, but I do have a video talking about this. What we do is, first off, make sure that your polynomial is in the form x squared plus bx plus c equaling 0. Make sure your leading coefficient is a 1. It has to be a 1, okay? And make sure it's set equal to 0. So we have that here. And by the way, in this problem, let's remind ourselves, a in this problem is 1, b is a 4, and c is -1. Sign comes with it. So the first step is we take the polynomial and I move the c over. So I've just added 1 to both sides. Okay? Now what I'm going to do is I'm going to take half of b and square it. So what is that? b is 4, so take half of that and square it. We get 2 squared, which is 4. Okay, what's the point of this number? What we're going to do is we're going to add that value to both sides of the equation. So I'm going to add a 4 here, and I'm going to add 4 to this side. Seems a little odd, but this problem is no different than this problem, and this problem is no different than the original. Hopefully you're seeing that. So we get an x squared plus 4x plus 4 equals 5. How on earth does this help us? Well, take a look at this left-hand side. This polynomial can now be factored down. We can, in fact, factor it into two binomials. What multiplies to give me 4 but adds to give me 4? Well, that's just positive 2 and positive 2. So we factor this polynomial down to get an x plus 2 squared equaling 5. Well, okay, but how are we going to solve this now? Well, actually, it's pretty easy. Take the square root of both sides. We get x plus 2 equals the square root of 5. And remember, we could have positive or negative values for that. And if I subtract 2 from both sides, I get -2 plus or minus the square root of 5. Remember, the square root of 5, we could have the positive or we could have the negative. That's when we're talking about actually evaluating an answer. I'm not checking an answer here. I'm just evaluating. And then I subtract 2 over, so I could have 2 plus root 5. I'm sorry, -2 plus root 5 or -2 minus root 5. Here are the two solutions. This is why we couldn't factor it before, because the solutions were radical answers. They contained a square root in them. And that's why we couldn't solve it before. What we do when we complete the square, this is the key idea. When we add this to both sides, we are forcing the polynomial to be able to be factored down. Let's take a look at another problem, and let's keep practicing these steps. First, it's in the form we want, so we're good to go. Then, I'm going to move the 5 over so I have a -5. I need to figure out what half of the middle term is, and then square that. Well, half of 4 is 2, and when I square it, I just get 4 again. So x squared plus 4x plus 4 equals -5 plus 4. Because what I add to one side, got to add to the other side. This can factor down into x plus 2 squared, and that's equal to -1. Okay. Now, let's take the square root of both sides. We get x plus 2 equals, well, wait a minute, what's the square root of -1? That's a complex number. That, in fact, is the complex number I. So, when I subtract 2 over, I get x equals -2 plus or minus I. These are the solutions that we're going to get for this problem. Notice that our answer now is in fact going to be a complex number. And that's totally fine. This problem Couldn't be factored down before. What multiplies to give us 5 but adds to give us 4? Couldn't factor it. I can't think of any numbers that do that. And in fact, the reason for that is because they're complex numbers. So hopefully this is making sense to you, this process. Again, I have a video explaining this for today. If you have any questions, feel free to let me know. What I'd like to do right now, before we sign off, is I'd like to quickly go and just review that we could, in fact, solve this problem that we had a minute ago by doing the completing the square technique. So let me clear some space. And we know that the solutions are 1 and 5, and in fact, those are both extraneous. So what I'm hoping to do is solve this quadratic using the completing the square method and still ending up with 1 and 5, those extraneous solutions. Okay, given this polynomial, I want to complete the square with it. Now, I can't go ahead and do that just yet. The reason is because this coefficient is not a 1. To complete the square, it's got to be a 1. So what do? How can I make that leading coefficient a 1? Well, very simple. If it's not a 1, all you have to do is divide both sides of the equation by that number. So we end up with a 1x squared minus 6x plus 5 equaling 0. All right, easy as that. This is true in any case when you have a polynomial where the leading coefficient is not 1. Just divide both sides by that coefficient, and there you go. I don't care how complicated these get, okay? You'll see in the video, these might even, in fact, turn into fractions. That's totally fine, all right? We have calculators, we have ways of working with that. The big thing is just making sure this leading coefficient is a 1. So we can start doing the completing the square method. I can move the 5 over, so it's negative 5. I then need to take the middle term b, which is negative 6. I need to cut it in half and square it. So negative 6 divided by 2 is negative 3. And when I square that, I get 9. So let's go ahead and let's add that to both sides. We end up with, well, the left-hand side can be factored down into x minus 3 times x minus 3, and that's equal to 4. So we have x minus 3 squared is equal to 4. And if I square root both sides, I end up with x minus 3 equals plus or minus 2. So adding 3 over, I get x equals 3 plus 2 or 3 minus 2. Well, 3 plus 2 is going to be a 5, and 3 minus 2 is a 1. So here we go. We, in fact, get the exact same solution as before. We just did it by completing the square. Well, I don't see any questions in the live chat or any comments about if anyone wants me to do anything else or review anything. So I think we'll probably bring this live stream to an end right now. If you do have questions or comments, or if you'd like me to go over anything, please let me know. My email is klinford, that's KLINFORD, at wccnet.edu. I will, in fact, have another live stream today at 2 o'clock. So let me know if there's anything in particular you'd like me to review or go over by then. And until next time, take care.